So in this video, I'm going to give you an introduction or basic overview of calculus. We're going to go over topics like graph and functions, the parent functions, some examples of transformations, limits, continuity, derivatives, and integration or antiderivatives. So those are going to be the main topics of this video. It might be a very long video, but it's going to give you a nice introduction for those who are taking calculus and for those who want a quick review. Now, for those of you who may want to find more videos on calculus, you can check out my channel page because this video won't cover all the topics. There's a lot more. It's just going to give you a brief overview. So check out my channel page if you want to find more videos. I do have more videos on algebra, trigonometry, pre-calculus, chemistry, physics, and organic chemistry. You can also check out my website, video-tutor.net as well, to find more videos and playlists. So let's go ahead and begin. Now the first function that you need to know is y is equal to x. It's a linear function and it's basically a straight line. The next function is y is equal to x squared. This is a parabolic or a quadratic function, and it looks like an upward U shape. It looks something like this. The next function that you need to know for calc is y is equal to x cubed. Now what do you think the parent function for this graph looks like? What do you think about it? I'm going to write up another one. The next one is the cube root of x. X cubed is an increasing function, and it looks like this. The cube root of x looks very similar to x cubed, but simply just rotate it. It's an increasing function, but it looks this way. Towards the end, it becomes horizontal as opposed to being vertical. Now here's another two examples for you. What about this one? Y is equal to 1 over x. And also, y is equal to 1 over x squared. What do you think the parent function for these graphs look like? 1 over x is an odd function in the sense that it's symmetric about the origin. 1 over x squared is an even function. It's symmetrical about the y-axis. So whenever you square a number, the result will always be positive. That's why this side is above the x-axis and not below it. And as you can see, the right side is a mirror image of the left side. So there's symmetry about the y-axis. Now what about this one? Y is equal to the square root of x as opposed to the cube root of x. The square root of x function looks like this. It's a function that increases at a decreasing rate. Now what about these two? E to the x and also the natural log of x. What's the graph for these two functions? E to the x is an exponential function that increases at an increasing rate. Notice that it starts from the x-axis. The x-axis is basically the horizontal asymptote. If you see like plus 2, it's going to be shifted up 2 units, and the horizontal asymptote will be y equals 2. Now, the natural log function has a vertical asymptote at x equals 0, as opposed to a horizontal asymptote. Now, this function increases at a decreasing rate. So if you look at the exponential function, it begins horizontally, and then towards the end, the behavior of the graph is vertical. It looks like it's going up. And for the natural log function, it begins vertically, and then it changes in the horizontal direction. These two functions are opposites of each other. It turns out that the e to the x function is the inverse of the natural log function. If you draw the line y equals x, you'll see that these two functions are mirror images of each other. So I'm going to draw the natural log function in purple, which, let's do that again. It looks like this. As you can see, these two graphs are symmetrical about the yellow line. So they're symmetrical about the line y equals x, which is the characteristic of inverse functions. When two functions are inverses of each other, f of g of x will equal x, and g of f of x will also equal x. That's how you can tell if two functions are inverses of each other. These are known as composite functions. Now, what if you were to see something like this? What's the parent function or the shape of the parent function? How would you draw a rough sketch for this graph? This is the absolute value function, and it basically forms a V shape. So that's the absolute value of x. Now, whenever you have an absolute value function, you can break it into two parts. You can turn it into a piecewise function, and notice that the right side is the same as positive x. The function is increasing with a slope of 1. And the left side is negative x. So this is true whenever x is greater than 0, and here when x is less than 0. Now, when it equals 0, it really doesn't matter, you could just pick one, but some teachers tend to pick this one when it equals 0. Now let's move on into trig functions. We're not going to cover all the trig functions, just a few of them. So the first one, y is equal to positive sine x. And how is that different from negative sine x? So whenever you're dealing with the sine function, sine starts at the center. Positive sine goes up, down, like back to the middle, down, and then back to the middle, and the cycle repeats itself. But let's just draw one cycle. Negative cosine starts at the center, but instead of going up, it's going to go down first, and then back towards the center. Now what about positive cosine and negative cosine? What do you think the shapes for these two graphs will look like? Now sine always starts at the center. As you can see here, cosine will start above the center or below it. So positive cosine starts above the center, and then it travels down towards the middle, and it forms a sinusoidal shape. Negative cosine starts below the center and goes up, and so forth. So now you know the general shapes of the trig functions sine and cosine. Now what about secant and cosecant? Let's start with secant. How can we graph secant? Secant is the reciprocal of the cosine function. So it helps to graph cosine first. Positive cosine is going to start from the top, it's going to go towards the middle, and then below it, back to the middle, and then back to the top. Now you can extend the graph if you want to. So let's draw another cycle. Now when drawing secant, identify the points where it reaches the center line, in this case the x-axis. Those points will be the location of the vertical asymptotes. And secant is the reciprocal of cosine. So what you want to do is draw the reciprocal of it. So secant is going to be represented by the yellow line, and it's going to stay within the vertical asymptotes. So that's how you graph the secant function. Simply draw the reciprocal of cosine. So now that you know how to do that, go ahead and graph cosecant, which is the reciprocal of the sine function. So let's begin by drawing positive sine, which starts at the center, and then it goes up. And let's draw two cycles. Identify the point where it touches the x-axis, which is basically the midpoint between the top part of the wave and the bottom. At the midpoints, these are going to be the vertical asymptotes. Now we can draw the cosecant function. So just draw the reciprocal of the sine function. So now you know how to graph the cosecant function. But what about tangent and cotangent? So let's start with tangent. There's two vertical asymptotes of tangent that you need to know. The first one occurs at negative pi over 2 and at x equals pi over 2. Tangent of 0 is equal to 0. Tangent is an odd function, kind of like x cubed. So that's how tangent looks like. Now cotangent is not an increasing function, it's a decreasing function. But cotangent is going to have a different vertical asymptote. It's not going to be negative pi over 2 and pi over 2. Rather, it's going to be 0 and pi. Also, 2 pi, 3 pi, negative 1 pi, negative 2 pi, and so forth. So cotangent is a decreasing function. So it looks like that. So now you know the parent functions of a lot of functions and graphs that you need to know for calculus. Now let's talk about transformations. Let's start with the graph y equals x squared. Now we know it's an upward parabola, which looks like this. So based on this information, how can we graph the function y is equal to negative x squared? How would you graph it? The negative sign in front of the x squared is going to cause it to open downward as opposed to upward. So it's going to reflect over the x-axis. So knowing that, what about these two graphs? Let's say if y is equal to x squared plus 4, and also if y is equal to x minus 2 squared. X squared plus 4, the graph is going to shift 4 units up, and because there's a positive sign in front of the x squared, it's going to open upward. X minus 2 squared from the right. If you set the inside equal to 0, and if you solve for x, you'll see that x is equal to 2. So it's going to start 2 units to the right, and it's going to open in the upward direction. Now what about this one? Let's say if y is equal to negative x plus 3 squared minus 4. How can we graph this function? So first, if you set the inside x plus 3 equal to 0, you'll see that x is equal to negative 3. So that means it's going to shift 3 units to the left. The negative 4 in front tells us that it's going to shift down 4 units. So the graph is going to start at negative 3, negative 4. Now we have a negative in front, so it's going to open downward. So the graph is going to look like this. I'm out of space, but that's where it's going to open towards. So now you know how to sketch a rough graph for parabolas using transformations. Now let's talk about square root functions. There's 4 graphs that we're going to go over. The first one is y is equal to the square root of x. The second one, y is equal to the square root of negative x. For the third one, y is equal to negative square root x. And the last one, negative square root negative x. So for the first one, both x and y are positive, which is true in quadrant 1. This is quadrant 1, quadrant 2, Q3, and Q4. So in the first one, it's going to go towards quadrant 1. Now the second graph, x is negative, but y is positive. X is negative on the left side, y is positive on top. So it's going to go towards quadrant 2. Therefore, we could say that it's reflected over the y-axis. Now for the next one, y is negative, but x is positive. X is positive towards the right side, y is negative below the x-axis. So this graph is going to go towards quadrant 4. So it's going to look like this. So this one reflects over the x-axis, and this one reflects over the y-axis. And what about the last one? So we have a negative in front of the x, and also in front of the radical, which is associated with y. So x is negative towards the left, y is negative below the x-axis, so it's going to go towards quadrant 3. So this graph is going to look like this. So it reflects about the origin relative to this graph. So now let's put it together. Go ahead and draw a rough sketch. It doesn't have to be drawn to scale, but you want to have the correct starting point and the appropriate direction. Draw a rough sketch of this graph, 5 minus the square root of x plus 3. By the way, if you want more examples on graphing functions, there is a video I created on YouTube entitled Parent Functions and Transformations. I believe that's the title, so you can look it up on YouTube. Or you can just visit my channel and find the video. It's in my algebra playlist. And you should also find it in my either my pre-calculus playlist or my calculus playlist as well. It might be my algebra playlist. Now that I think about it, it may or may not be there, but it should be in my pre-calculus playlist. So we can see that the function is going to shift 3 units to the left, and it's going to shift 5 units up. Now notice that we have a positive sign in front of x, so it's going to go towards quadrant, it's going to go towards the right, and there's a negative in front of the radical, so it's going to go down. That is towards quadrant 3. But the first point is at negative 3, comma 5. And whenever it goes towards quadrant 3, it's going to move like this. So this is going to be the graph of the function. Now let's talk about limits. So let's say if we have a function x squared plus 2x minus 5, and we wish to evaluate the limit as x approaches 2 for the function f of x. How can we do so? The limit as x approaches 2 is not exactly the same as f of 2. Rather, you're going to plug in a number that's very, very close to 2. For example, like f of 1.999. The limit as x approaches 2, you want to get as close as to 2 as possible, but not exactly to 2. Now, if we plug in 1.999, it's going to be very close to 2. In a situation like this, if you can use direct substitution, go ahead. So the limit as x approaches 2 for this function, just plug it in. Unless you get like a 0 in the denominator, then you're going to have to do something else. But if you can plug it in, always use direct substitution. 2 squared is 4, 2 times 2 is 4, 4 plus 4 is 8, 8 minus 5 is 3. That's the answer. Now sometimes you can't use direct substitution. Let's say if we have the function the limit as x approaches 3, x squared minus 9 divided by x minus 3. If we plug in 3, 3 squared is 9, and 3 minus 3 is 0. So we have 0 over 0, which is indeterminate, so we can't use direct substitution like this. However, we can use direct substitution in a different way. Let's plug in two numbers that are close to 3, 3.1 and 3.01. So let's calculate f of 3.1. So that's going to be 3.1 squared minus 9 divided by 3.1 minus 3. So let's use a calculator for this. 3.1 squared is 9.61 minus 9, so that's about 0.61. And 3.1 minus 3 is 0.1. 0.61 divided by 0.1 is 6.1. Anytime you divide by 0.1, multiply that number that you're trying to divide by 10. Now let's try a number that's closer to 3, 3.01. The closer you get to 3, the more accurate the answer will be. So let's type in 3.01 squared minus 9 divided by 3.01 minus 3. So 3.01 squared is 9.0601 minus 9. This is equal to 0.0601 divided by 0.01. When you divide by 0.01, multiply the numerator by 100. So you should get 6.01. So the true answer is actually closer to 6 than it is to 6.1. To find the true answer, we can factor the numerator. So we have the difference of perfect squares. To factor x squared minus 9, it's going to be x plus 3 times x minus 3. We can cancel these two terms. Now that this factor is gone, which gave us a 0 in the denominator, we can now use direct substitution. So let's replace 3 into the surviving part of the equation, that is the x plus 3. So that's going to be 3 plus 3, which is equal to 6. So the exact answer is 6. And as you can see, as x gets closer to 3, the y value approaches 6. Going from 6.1 to 6.01, you could see that it's converging to 6. And that's what the limit allows us to do. It allows us to calculate the y value of a function as we approach a certain value. Notice that we approached 3, but we never quite actually got to 3. Because if you plug in 3 into this function, it's undefined. If you were to graph it, the graph is going to look like y equals x plus 3, but with a hole at positive 3. So it's going to look something like this. Now let's try another example using radicals. Let's say if we have the limit as x approaches 16, square root x minus 4 divided by x minus 16. So can we use direct substitution? If we plug in 16, 16 minus 16 is equal to 0. And if we have a 0 in the denominator of a fraction, it will be undefined. So we don't want to do that. Instead, let's use direct substitution, but with a number that's close to 16. So let's try 16.1 and 16.01. The square root of 16.1 is about 4.01248 minus 4 gives you this number. There's more numbers after the 8, but I'm going to round it. Divided by 0.1. 16.1 minus 16 is 0.1. So this is about 0.1248. And if we plug in 16.01, the square root of 16.01 minus 4, not 16, that's 0.0012498. And then 16.01 minus 16 is 0.01. So this is 0.12498. So let's get the exact answer. As you can probably see, this is appearing to approach 0.125. But let's see if we can get an answer that's close to those numbers. So what can we do to get the exact answer? Whenever you have radicals, multiply by the conjugate of the radical. What is the conjugate of the expression square root x minus 4? It's going to be the same thing, but instead of a negative sign, we need to change it to a positive sign. So it's the square root of x plus 4. And whatever you do to the top, you must also do to the bottom. on the numerator, we're going to FOIL the two expressions. But on the denominator, we're just going to leave it the way it is. So the square root of x times the square root of x is the square root of x squared, which is simply x. Now these two terms, positive 4 times root x and negative 4 times root x, will cancel. They will add up to 0. Negative 4 times 4 is equal to negative 16. So notice that we can cancel the factor on the bottom that gave us a 0. Once this disappears, we can now use direct substitution. By the way, in your course, you may have to rewrite the limit expression for every step. Some teachers will take off points for this. So now that we have this expression, let's plug in 16. So once you plug it in, you don't need to rewrite the limit expression. The square root of 16 is 4. And so we have 4 plus 4, which is 8. And 1 over 8, if you type this in the calculator, the exact answer for 1 over 8 is 0.125, which we saw it was convergent to this number. So as you can see, for any limit problem, if you have access to a calculator, if you're allowed to use it, you can always use direct substitution with a number that's close to the number that you're trying to approach. It will always work unless you make a calculator mistake. If you mistype it in your calculator, then I don't know what to say about that, but just be careful. If you plug in everything correctly, you should get the right answer. Now let's try another example. What is the limit as x approaches 3? For this function. So first, let's get the answer using direct substitution with a number that's close to 3. So let's try 2.99. We're going to plug it in once instead of 2 times, now that you understand the process. 1 divided by 2.99 is about 0.334448 minus 1 over 3. You should get this number, 0.001114827. And then 2.99 minus 3, that's negative 0.01. So this should give you negative 0.11148. Now, this might be negative 0.1 repeating. Negative 0.1 repeating is negative 1 over 9. So let's see if we get that answer. To confirm that the limit exists, plug in another number, like maybe 2.999. And if you see that it's convergent to negative 0.1111, you're on the right track. If it changes completely, the limit may not exist. Now, whenever you have fractions, you want to multiply the top and the bottom by the common denominator of the smaller fractions on top. So that is 3x. Now, if we take the first fraction, 1 over x, and multiply it by 3x, the x variables will cancel, leaving behind only 3. 1 over x times 3x is equal to 3. Now, 1/3 times 3x, the 3's will cancel, leaving behind x. And on the bottom, we have x minus 3 times 3x. Can we cancel these two expressions? What would you say? Yes, but you need to be careful. They don't completely cancel. I would suggest modifying it first before canceling it. In the numerator, let's take out a negative 1 sign. If we factor out negative 1, negative x will change to positive x. I'm going to reverse it, by the way. Positive 3 changes to negative 3. So, as you can see, when you divide 3 minus x by x minus 3, it's equal to negative 1. So what we have left over is the limit as x approaches 3, negative 1 over 3x. So now we can plug in 3. So if we replace x with 3, 3 times 3 is 9. So this is negative 1 over 9, which is equal to negative 0.111 repeating, or just 0.1 repeating. Now let's work on analyzing limits using a graph. So let's say if you want to calculate the limit as x approaches -3 from the left side. And let's say that this graph represents the function f of x. What would you do in a problem like this? To evaluate this, you need to look for the y value. So first, look for -3. -3 is in this region. Imagine a vertical line at -3. It's in that region. Now there's 3 points of interest. This point, which has a y value of 3, this point, which has a y value of 1, and this one, which has a y value of -2. We're interested in -3 from the left side. This is the only curve that is associated with the left side of -3. So as we approach -3 from the left side, we can see that the y value is equal to 1. So that's how you can evaluate a one-sided limit. Now what about the limit as x approaches -3, but from the right side? So this part occurs at x equals -3, and it has the right side of the curve at -3. So as we approach -3 from the right side, the y value is equal to -2. Now what about the limit as x approaches -3 from either side? What's the answer for this? To answer this question, look at the one-sided limits, which are these two. So on the left side, the y value is 1. On the right side is -2. If the left-sided limit and the right-sided limit does not match, the limit does not exist. So unless these two connect, if there's like a jump discontinuity, the limit will not exist. By the way, we're going to talk about continuity as well. So since we have this graph, it might be a good time to talk about it. So anytime the curve disconnects, you have some type of discontinuity. What we have here is a jump discontinuity. Notice that the curve breaks between these 2 points. If it's associated with a vertical line or a vertical asymptote, it's an infinite discontinuity. And here, this is a hole, which is also known as a point discontinuity. Point discontinuities are known as removable discontinuities. Jump discontinuities or infinite discontinuities are non-removable. If you recall in an earlier example, the one with x squared minus 9 over x minus 3, it produced a point discontinuity because we were able to remove or factor out one of the terms. I believe it was x minus 3. Now there's one more question that we have with this particular x value. Now what about f of -3? What is that equal to? So what is the y value when x is exactly equal to -3? To answer this question, look for the closed circle. The closed circle is here, and look for the y value. The y value is 3. So f of -3 is equal to 3. Now let's try another example. What is the limit as x approaches 1 from the right side? What would you say? So x equals 1 at this point. Now we wish to approach it from the right side. So look for the y value. The y value is -1. Now what about the left side? As we approach x equals 1 from the left side, what is the y value there? Notice that from the left side, it's still the same. It's about 1. So therefore, what is the limit as x approaches +1 from either side? Because the left side and the right side are the same, the limit exists. it is also equal to 1. Now what about f of negative 1? I mean positive 1. What is the value of f of 1? Notice that there's no closed circle at an x value of 1. Therefore, it does not exist. By the way, if you want more examples on limits, you can do a search on YouTube. There's a video I created that is entitled One-Sided Limits. Or you can just go to my channel and look for my calculus playlist. It also has limits as well, plus other topics. Now, let's try some more examples. What is the limit as x approaches positive 2 from the right side? And while you work on that, I'm going to write a few more. What is the limit as x approaches 2 from the left? And what is the limit as x approaches 2 from either side? And also, what is f of 2? So as we approach 2 from the right side, notice that the y value is equal to 1. As we approach 2 from the left side, the y value is still equal to 1. So therefore, the limit as x approaches 2 from either side is 1. And also, we have a closed circle, so f of 2 is 1. Whenever the limit equals the function at that point, it is continuous at that point. When the limit exists, but the function does not exist, we have a point discontinuity. So keep those things in mind. They might be useful to you in the future. I'm pretty sure they will. Now, what about the limit as x approaches negative 1 from the left side, and also the limit as x approaches negative 1 from the right side, and also the limit as x approaches negative 1 from either side, and f of negative 1. So notice we have a vertical asymptote. Now let's focus on the left side. As we approach 1 from the left, the graph is going up towards positive infinity. Now on the right side, as we approach 1, it goes down towards negative infinity. Because these two do not match, the limit does not exist. And f of negative 1, there is no closed circle on its vertical asymptote, so this does not exist. So it's not continuous at x equals negative 1. These two do not exist. The function has to be defined for it to exist, or it to be continuous at that point. Now sometimes you may need to determine if a function is continuous or discontinuous without the use of a graph. And typically you might be given a piecewise function. And in situations like this, it's helpful to use the three-step continuity test. So step 1, the function must be defined at some point a. So f of a has to be defined. Now step 2, the limit has to exist. The limit as x approaches a for the function f of a exists. And for it to exist, the left side and the right side limits must equal each other. So therefore the limit as x approaches a from the left side of f of x must equal the limit as x approaches a from the right side of the function f of x. Step 3, the limit as x approaches a, f of x has to equal f of a. So if that's true, then the function is continuous at that point. So let's work on an example. Let's say that f of x is represented by this piecewise function. We have x plus 6, x squared, and 5x minus 1. For the first part, let's say that x is less than or equal to negative 2. And for the second part, let's say x is greater than negative 2 but less than 3. And for the last part, let's say that x is greater than or equal to 3. Our goal is to find the point of discontinuity. And we can do that using a 3-step continuity test if we need to justify our answer. But let's do it the quick way first. By the way, look at each piece of the function. And sometimes you have to look out for rational functions, radicals, natural logs, and things like that. Because let's say if you have a radical function, for example, like 1 over x minus 3, the function is undefined at x equals 3. There's a vertical asymptote, so automatically you know it's an infinite discontinuity. To review this topic, look at my video on YouTube on domain and range. It helps you to find out how to write the domain of a function. Whatever is not in the domain, the function does not exist there. So it can help you to find out points of discontinuities. Now going back to this, linear functions like x plus 6 and 5x minus 1 is continuous everywhere. And the same is true for quadratic functions like x squared or any polynomial expressions. However, when we have a piecewise function, at negative 2, the y value may not be the same. And at 3, it may not be the same. So if you have a multiple choice test and you don't need to justify your answer, you simply need to find the answer the quickest way possible, here's what you need to do. Plug in negative 2 into these two expressions. If they equal the same thing, then it's continuous at negative 2. So for example, negative 2 plus 6 is 4. Negative 2 squared is 4. Because they equal the same y value, the function is continuous at negative 2. Now, let's plug in 3 into these two expressions. 3 squared is equal to 9. 5 times 3 minus 1 is 15 minus 1, which is 14. So these two don't match. Therefore, it is discontinuous at x equals 3. That's the quick way to find the answer. Now, to justify the answer, if you have a free response question, you want to use the 3-step continuity test. So let's prove that it's continuous at negative 2. So first, let's determine that the function is defined. So let's find the value of f of negative 2. To find f of negative 2, should you use this expression or this expression? Keep in mind, on a graph, you're looking for the portion that has the closed circle. So which graph contains the value x equals negative 2? For this one, x does not equal negative 2. X is greater than negative 2. But for this one, x can be equal to or less than negative 2. So we need to use this expression. So it's going to be negative 2 plus 6, which is equal to 4. So the function is defined at negative 2. So step 1 is okay. So you can put a check for that if you want to. Now step 2, we need to prove that the left side and the right side of limits are the same. So let's start with the left side. The limit as x approaches negative 2 from the left. From the left, that means less than negative 2. We need to use this expression. So that's going to be negative 2 plus 6, which is 4. Now for the right side, the limit as x approaches negative 2 from the right, that's greater than negative 2. We need to use this expression. So that's going to be negative 2 squared, which is 4. So because the left side and the right side are the same, the limit exists. So we can make the statement that, let me erase this. So we can say that the limit as x approaches negative 2 of the function f of x is equal to 4, because the left side and the right side matched. Now step 3, we can make the statement that these two are equal to each other. That is, the limit as x approaches negative 2 of f of x is equal to f of negative 2. So that's step 3. If each of these are true, then you've proven that the function is continuous at x equals negative 2. Now let's focus on x equals 3. Let's prove that it's discontinuous. So let's go through the process. Let's start with step 1. So is the function defined at 3? So what is f of 3? Now we can't use this expression because x is less than 3 but not equal to 3. Here x is equal to 3. So we need to use 5x minus 1. So it's 5 times 3 minus 1, which is 16. So the function is defined at x equals 3. Now, step 2. We need to show that the left side and the right side of limits are the same. So the limit as x approaches 3 from the left side, we need to use x squared. So 3 squared is 9. And the limit as x approaches 3 from the right side, which is 5x minus 1. So that's 5 times 3 minus 1. Oh, wow. 5 times 3 is 15 minus 1 is 14. It's not 16. That's a bad mistake. So let's correct that. Either case, for number 1, it's still defined, but for number 2, they don't match. So therefore, we can say that the limit as x approaches 3 from either side does not exist. So step 2 has failed. For the function to be continuous at that point, the limit must exist. So therefore, the function is discontinuous at x equals 3. So that's the 3-step continuity test, and that's how you can apply it. The best way to master this concept is to practice it with problems in your textbook. So now let's move on to another topic, but still within continuity. Now you might see a question like this sometimes. Let's say that f of x is equal to cx plus 3 and cx squared minus 7. For the first one, when x is less than 2, and for the second one, when x is equal to or greater than 2. Find the value c such that the function is continuous at x equals 2. If you get a question like this, what you need to do, well, first, feel free to pause the video and try it. See if you can figure it out. If you're ready, unpause it and watch the solution. Now, what you need to do for this problem, to make it continuous, these two parts must have the same y value. Therefore, set them equal to each other. Cx plus 3 should be equal to cx squared minus 7. And to find the value of c, insert x, or a value of x with 2. Replace x with 2. Sometimes I'm at a loss for words. So c times 2 plus 3 is equal to c times 2 squared minus 7. So we have 2c plus 3. 2 squared we know is 4. And just solve for c at this point. So let's subtract both sides by 2c. And at the same time, let's add 7 to both sides. So 3 plus 7 is 10. 4c minus 2c is 2c. And now let's divide by 2. 10 divided by 2 is 5. So c is equal to 5. At this c value, the function will be continuous at x equals 2. Use the intermediate value theorem to show that there is a root of the given equation in the specified interval. So what is the intermediate value theorem, or the IVT theorem? The intermediate value theorem basically states this. If the function is continuous on the closed interval a to b, such that n, or some number, is between f of a and f of b, and also if c is between a and b, then f of c must equal that number n. So let's talk about this expression, or this definition, in graphical terms. So we're concerned about finding some x value that is a root of the given equation in the interval. So that's the c value we're looking for. So the c value has a y value of 0. So f of c is 0. Let's say it's between a and b. if f of c is 0, then we need to show that f of a is either a negative or a positive number. Let's say f of a is a negative number. Let's say it's somewhere over here, and f of b is a positive number. If f of b is greater than 0, and if f of a is less than 0, then at somewhere between a and b, the function has to pass through the x-axis. It has to pass through 0. So as long as f of a is negative and f of b is positive, or the other way around, f of c, there has to be a c value where f of c is equal to 0. If the function is continuous, to go from a negative value to a positive value, it has to cross 0. So here's what we need to do to show our work. So first, find the values of f of 1 and f of 3. Let's start with f of 1. That's 1 squared plus 1 minus 6. 1 plus 1 is 2, 2 minus 6 is negative 4. So we have a negative value here. Now let's calculate our f of 3. So 3 squared plus 3 minus 6. 3 squared is 9. 9 plus 3 is 12. 12 minus 6 is positive 6. So, and we know that f of c has to be equal to 0 because it's a root of the given equation, and the y value is 0, as we can see. So 0 is between negative 4 and 6. Therefore, there must be a c value that's between a and b. A is 1, b is 3. So there must be a c value between 1 and 3. So let's go ahead and solve for x. The answer that is between 1 and 3 is the c value that we're looking for, according to the intermediate value theorem. Now we can factor this expression. What number multiplies to negative 6 but add to positive 1? 3 and negative 2. 3 times negative 2 is negative 6. 3 plus negative 2 is plus 1. So we can factor as x plus 3, x minus 2. Now let's set each factor equal to 0. And let's solve for x. So therefore x is equal to negative 3 and x is equal to 2. Now which x value is the c value that we're looking for? Negative 3 is not between 1 and 3. So therefore we don't want this value. 2 is between 1 and 3. So this is the value we want. So therefore c is equal to 2. Consider this particular graph. Now what would you do to calculate the slope of this line? How can we find the slope of the line? To find the slope, you can use the technique rise over run. Going from the first point to the second point, the graph went up by 3 units and it traveled 2 units to the right. So the slope is 3 over 2, which is rise over run. You can also calculate the slope using this equation, y2 minus y1 divided by x2 minus x1. This equation is useful in calculating the average rate of change. The average rate of change, which is the same as the slope, I'm going to write AROC for average rate of change. It's equal to f of b minus f of a divided by b minus a. You'll see this formula in calculus. And it's basically the same formula as the slope. The average rate of change is basically the slope of the line between 2 points. So as we can see, this point here is x is 2, y is 4, and for the other one, x is 0, y is 1. So y2 is 4, y1 is 1, x2 is 2, x1 is 0, 4 minus 1 is 3, 2 minus 0 is 2. The average rate of change, or the slope between those 2 points, is 3 over 2. Now, whenever you have a linear function, the slope is constant. But what about if we don't have a linear function? Let's say if we have a parabolic function y equals x squared. What is the slope at x equals 0? Let's say at x equals 1, x equals 2, -1, and -2. How can we find the slope at these different points? The slope on the right is positive, on the left is negative. Whenever you have a horizontal line, the slope is 0. If you have a line that rises at a 45-degree angle, the slope is 1. So here we could say this is approximately 2. Whenever the line goes down, the slope is negative. And whenever you have a vertical line, the slope is undefined. 1 divided by 0 is undefined. So on the right side of the graph, the slope is positive. On the left side, the slope is negative. And in the middle, we can see that we have a horizontal tangent, and the slope at that point is 0. So how can we find the slope of this function at any x value? How can we find the slope when x is 1, when x is 2? Enter derivatives. Derivatives are functions that can help us to calculate the slope at any point x. The original function f of x is equal to x squared. The derivative, represented by this symbol, f prime of x, is equal to 2x. If we plug in 0, the derivative when x is 0 is 0. Thus, the slope is 0 at that point. When x is 1, the slope is equal to positive 2. And we can see that at 1, the function is increasing. At 2, the slope is going to be 2 times 2, or positive 4. On the left side, at -1, the slope is -2. We can see that the function is decreasing at this point. So as we could see, the derivative is a function that tells you the slope of the curve of f of x at any point x. Because when you have a parabolic function, the slope changes. The slope is only constant for a linear function. So what does the slope represent? The derivative gives you the slope at a single point, which represents the instantaneous rate of change. The first slope equation that we use, y2 minus y1 over x2 minus x1, that was between 2 points, and that is equal to the average rate of change. F of x, let's say it's x cubed. The derivative of this function is 3x squared. Now we know that this graph looks like this. Now let's say if we want to find the instantaneous rate of change. You need to know that the instantaneous rate of change is equal to the slope of the tangent line. The tangent line is a line that touches the curve at a single point. Now, the secant line is a line that touches the curve at 2 points. You can estimate the slope of the tangent line using the slope of the secant line. We're going to do that in this example. So just remember this, the slope of the secant line is equal to the average rate of change. The slope of the tangent line is equal to the instantaneous rate of change. So anytime you need to find the instantaneous rate of change, find the first derivative and plug in the value. That will give you the slope of the tangent line. Anytime you need to find the average rate of change, use the slope formula, y2 minus y1 over x2 minus x1, which is equal to f of b minus f of a over b minus a. So let's calculate the instantaneous rate of change when x is equal to 3. So we need to find f prime of 3. So using this formula, it's going to be 3 times 3 squared, which is 3 times 9, that's 27. So the slope of the tangent line, which is the instantaneous rate of change, is 27. Now let's see if we can estimate the value using the average rate of change formula. So let's calculate the average rate of change between, or in the interval 2 to 4. So it's going to be f of b, or f of 4, minus f of a, or f of 2. A is 2, b is 4, divided by b minus a, or 4 minus 2. So if we plug in 4 into, not that formula, but the original function, this is going to be 4 cubed minus 2 cubed. 4 minus 2 is 2. 4 to the third is 64. 2 to the third is 8. 64 minus 8 is equal to 56. And 56 divided by 2 is 28. So as you can see, these two values are very close, but not exactly the same. So the average rate of change can be used to approximate the instantaneous rate of change. But the answer can be more accurate if we choose two numbers that are closer to 3. So instead of using 2 and 4, let's use 2.9 and 3.1, such that 3 is in between 2.9 and 3.1. The closer we get to 3, the more accurate the answer will be. The average rate of change will get closer to the instantaneous rate of change. So f of 3.1 minus f of 2.9 divided by 3.1 minus 2.9. So this is 3.1 to the third power minus 2.9 to the third power divided by 0.2. 3.1 cubed is about 29.791. 2.9 to the third power is 24.389. The difference between the two numbers on top is 5.402. If you divide it by 0.2, it's going to give you 27.01, which is a good approximation for the instantaneous rate of change. Now let's understand why it becomes more accurate as you move closer to the point of tangency. So let's look at the graph of x squared. Let's say we want to find the slope of the tangent line at this point. Remember, the tangent line is a line that touches the curve only at one point. Now if we pick 2 points that are far away, notice that the slope won't be the same, especially since this point is not in between the x values of those two other points. So let's make our second point. Here. So now this point is in the middle between the two green points. But even still, you can see that the slope is not the same, but it's more accurate than the last example. Now, as these 2 points move closer to the point of tangency, that is the yellow point, you'll see that the slopes of the two lines, the secant line, which touches the point at 2 curve, and the tangent line, the slopes will be the same. They will appear parallel to each other. So let's pick 2 points that are closer, such that the yellow line, or the yellow point, is in between the 2 blue points. So if we connect these 2 points with a line, notice that the slope is more accurate, so to speak. Maybe I should draw this line better. This should be more like this. My tangent line may not be that accurate. So here's the tangent line. And let's pick 2 points close to it. So as you can see, the slope of these 2 lines is almost the same as the slope of the tangent line. They appear to be parallel. And as the 2 blue points move closer to the yellow point, the slope of the secant line becomes a good approximation of the slope of the tangent line. So just make sure you remember this. The slope of the tangent line is equal to the instantaneous rate of change. And you can calculate this by finding the first derivative and plugging a value. Let's say the value is a. The slope of the secant line, which is the slope between 2 points instead of 1 point, the slope of the secant line is the same as the average rate of change. And you can find that by using this equation, f of b minus f of a over b minus a. And to find it, you need 2 points as opposed to 1 point. The next thing that you need to know is how to find the derivative of a function. Let's talk about the power rule. If you have a function in this form, x raised to the n, where n is a constant, x is a variable, the derivative of that function is going to be n times x raised to the n minus 1. So the derivative of x squared is 2x to the first power. The derivative of x cubed is 3x to the second power. For x to the fourth, it's going to be 4x cubed, and for x to the fifth, it's 5x to the fourth power. So with that in mind, how can we find the derivative of 4x to the seventh power? Ignore the constant in front. Let's differentiate x to the 7. So this is going to be 4 times 7x to the 6. And then at this point, multiply 4 by 7. 4 times 7 is 28. So the derivative of 4x cubed is, 4x to the 7th is 28x to the 6th. Now what about this one, 5x to the 8th power? Go ahead and find the derivative of the function. Feel free to pause the video. And also work on this example too, 6x to the 10th. So the derivative of x to the 8th power is 8x to the 7th power. And then multiply 5 times 8, which is 40. So this is it. For the second example, the derivative of x to the 10th is 10x to the 9. And 6 times 10 is 60. So it's 60x to the 9th. Now what if we have a constant? By the way, if you see this simple, d dx, it means that you're differentiating some expression with respect to x. So this is equal to 3x squared. This means that the derivative of x cubed is 3x squared. If you differentiate, let's say, y cubed with respect to x, it's going to be 3y squared times dy dx. But if you differentiate x cubed with respect to x, it's 3x squared times dx over dx, which cancels, and it's just 3x squared. If you differentiate with respect to r, let's say s to the 7th power, it's going to be 7s to the 6th power times ds over dr. Hopefully you see a pattern here. So I'll give you one more example. If you differentiate, let's say, z to the 4th with respect to t, it's going to be 4z cubed dz dt. Now, what is the derivative of a constant? Let's say the derivative of 3. What is that equal to? Now, if you recall, the derivative gives you the slope of the function at some value of x. If we graph y equals 3, this is going to be a straight line at 3. And the slope of a straight line is 0. Therefore, the derivative of any constant is always 0. At any x value, the slope will be 0. So the derivative of negative 24, which is a constant, is also 0. If you don't see any variables, it's going to be 0. What about the derivative of e and the derivative of pi? E is not a variable. E is a number. It's 2.718 and a bunch of numbers after that. So the derivative of E is 0. Pi is also a number, 3.14, and some more numbers after that. So this is also equal to 0. Now what about square roots and radicals? What is the derivative of the square root of x? If you have a radical function, rewrite it. The index number is 2 if you don't see anything here, and this is 1. So you can rewrite it as x to the 1/2. And then use the power rule. You can move the 1/2 to the front, and then subtract the exponent by 1. 1/2 minus 1 is the same as 1/2 minus 2 over 2, and 1 minus 2 is negative 1. So this is negative 1/2. Now, whenever you have a negative exponent, you can move the x variable from the top to the bottom, making the exponent positive instead of negative. So this is the same as 1 over 2 x to the positive 1/2. Now, if you recall, x to the 1/2 is the same as the square root of x. So we can leave our final answer as 1 over 2 square root x. You may want to jot this answer down because we're going to come back to it later in this video. So go ahead and try this one. What is the derivative of the cube root of x to the 5th power? Feel free to pause the video and work on this example. So the first thing we need to do is rewrite the function. This is the same as x to the 5/3. So let's move the exponent to the front. It's going to be 5/3 x, and then subtract the exponent by 1. So 1 is the same as 3 over 3. 5 minus 3 is 2. So this is going to be to the 2/3. Which, if we want to, we can rewrite it as 5 cube root x squared divided by 3. So now you know how to differentiate radical functions and square roots. Now what about rational functions and fractions? So if f of x is equal to 1 over x, then f prime of x is equal to what? So let's rewrite it. 1 over x is equivalent to x to the minus 1. Now let's find the first derivative. Let's move the exponent to the front, and let's subtract it by 1. Negative 1 minus 1 is negative 2. Now let's rewrite it. This is equivalent to negative 1 over x squared. So that's the first derivative of the function. Try this one. Differentiate 1 divided by x squared. So first, let's rewrite it. This is the same as x to the minus 2. Now let's move the negative 2 to the front. So it's negative 2x to the, and then subtract negative 2 by 1, which is negative 3. So it's negative 2x to the negative 3, which you can rewrite it as negative 2 divided by x to the positive 3. So now you know how to differentiate rational functions. Let's try one more example. If f of x is equal to 8 over x cubed, what is f prime of x? What is the first derivative? So first rewrite it. And then let's move the 3 to the front. So this is going to be 8 times negative 3x to the negative 4. And then that's equal to negative 24 divided by x to the 4th power. So that's the answer. That's the derivative. Now let's say that f of x is x squared. How can we prove that f prime of x is 2x using the limit definition of the derivative? Here's the formula using limits. F prime of x is equal to the limit as h approaches 0, f of x plus h minus f of x divided by h. Now, even though you know how to find the derivative using the power rule, sometimes you may get a free response question that asks you to use the limit process or the definition of the derivative to find the derivative. So you may have to use this formula to show that this is indeed the derivative of x squared. So how can we apply it? So we know what f of x is equal to. f of x is x squared. But what is f of x plus h? If f of x is x squared, f of x plus h is x plus h squared. So putting it all together, f prime of x is going to be the limit as h approaches 0, f of x plus h, which is this, minus f of x, which is the original function, divided by h. So let's make some space. So what do you think we should do in this problem? The first thing we should do is FOIL x plus h squared. That's the same as x plus h times x plus h. So x times x is x squared, and then x times h is xh plus another xh. That's 2xh. And then we have h times h, which is h squared, minus x squared. And let's not forget to rewrite the limit expression. So we can cancel these two. After that, we have the limit as h approaches 0, 2xh plus h squared over h. Now, in our next step, what we're going to do is take out an h. Let's factor it out of the equation. So it's going to be h times 2x plus h divided by h. And so these will cancel. Once you get rid of the h on the bottom, you can now use direct substitution. So you can replace this h with 0, and thus you get 2x, which is what we had before. So that's how you can use the limit definition to prove it. Now let's work on our next example. We said that when f of x was x or square root x, f prime of x was equal to 1 over 2 root x. Use the limit definition to show that this is indeed the derivative of the square root of x. So f prime of x is equal to the limit as h approaches 0, f of x plus h, which is going to be the square root of x plus h, minus f of x, which is just square root x, divided by h. So do you remember what we need to do whenever we have a limit with square roots? If you recall, we need to multiply the top and the bottom by the conjugate. So if you see a minus sign, change it to a positive sign. That's going to be the conjugate. And whatever you do to the top, you must also do to the bottom, so you don't change the value of the fraction. So let's FOIL the two terms that we have on top. The square root of x plus h times the square root of x plus h is going to be equal to x plus h, which we don't really need a parentheses for that. Now the two middle terms will cancel. Root x plus h times root x will cancel with negative root x and root x plus h. And then the last two, negative root x times root x, is simply negative x. On the bottom, we're just going to rewrite what we have. So at this point, we can cancel x. Positive x and negative x adds up to 0. So we have the limit as h approaches 0, h on top, h on the bottom, and then root x plus h plus root x. So now we can cancel an h. So what we now have is the limit as h approaches 0, 1 divided by the square root of x plus h plus square root x. So now we can use direct substitution. We can replace h with 0. And we don't need to rewrite the limit expression at this point. X plus 0 is simply x. So we have the square root of x plus the square root of x, where the coefficient is 1. And 1 plus 1 is 2. So our final answer is 1 divided by 2 square root x. Now let's try another example. We said that if f of x is 1 over x, f prime of x will be negative 1 over x squared. Go ahead and prove it using the limit definition. So f prime of x is equal to the limit as h approaches 0, f of x plus h, which is 1 divided by x plus h. So all you do is replace x with x plus h, and then f of x is simply what we have here. That's just 1 over x divided by h. So whenever we have a complex fraction, that is fractions within fractions, the best thing to do is to multiply the top and the bottom by the common denominator, which is these two. So we're going to multiply it by x and x plus h. So if we multiply these two, we can see that the x plus h term will cancel, leaving behind x. And if we multiply these two, we can see that x will cancel, leaving behind x plus h. So it's minus x plus h. And on the bottom, we're just going to rewrite what we have, which is h, x, and x plus h. And let's rewrite the limit as h approaches 0. So now we need to distribute the negative sign. So this is equivalent to the limit as h approaches 0, x minus h over everything that we have on the bottom. So x minus x is 0, so we now have the limit as h approaches 0, negative h divided by h, x, and x plus h. So now we can cancel h. So therefore we have the limit as h approaches 0, negative 1 over x, x plus h. So once we get rid of this h, we can now use direct substitution. So this is negative 1 over x times x plus 0, and x plus 0 is the same as x, and x times x is x squared. So now we have the final answer, negative 1 over x squared. Now let's say that f of x is x cubed. We know that f prime of x is 3x squared. Let's say that a is equal to 4. That means f prime of 4 is going to be 3 times 4 squared. 4 squared is 16 times 3 is 48. How can we use the limit definition to get this answer? You can use the same formula to get this value and then plug in 4 to get 48. Or you can use the alternative form of the definition of the derivative, which is this equation. F prime of a is equal to the limit as x approaches a, f of x minus f of a over x minus a. The other limit definition formula gave us a function in terms of x. This formula is going to give us a number, specifically 48 when a is 4. So f prime of 4 is equal to the limit as x approaches a, where a is 4. And this is going to be f of x, which is x cubed, minus f of a. So if we plug in 4 into this formula, 4 to the third is 64, divided by x minus a, or x minus 4. So our goal is to get 48 for this answer. So what can we do to simplify this limit? So we've used direct substitution. We've used the conjugate method, multiplying by the common denominator. The last thing we could do is factor. How can we factor x cubed minus 64? To factor it, we can use this formula. A to the third minus b to the third is equal to a minus b times a squared plus 2ab plus b squared. So a cubed is x cubed, b cubed is 64. So if a to the third is x cubed, a is x. If b to the third is 64, that means b is the cube root of 64, which is 4. So a squared is x times x, or x squared, plus 2ab, or actually that's not supposed to be 2ab, I take that back. That's supposed to be just ab. A times b, 4 times x, is just 4x. And then b squared, that's 4 squared, which is 16. So this expression is equal to what we have here. So therefore, we have the limit as x approaches 4, the expression that we have, divided by x minus 4. So once we get rid of the x minus 4, we can now use direct substitution. So let's replace 4, or let's replace x with 4. So it's going to be 4 squared plus 4 times 4 plus 16. 4 squared is 16, 4 times 4 is 16, and 16 plus 16 plus 16 is basically the same as multiplying by 16 times 3, which is 48. So notice that we get the same answer in this particular example. Now let's move on to exponential functions. How can we find the derivative of e to the 4x? Now there's a formula for this. If you wish to differentiate, let's say e to the u with respect to x, where u is a function in terms of x, it's going to be the same thing, e to the u times u prime, which is the derivative of u. So it's going to be the same thing, e to the 4x times the derivative of 4x, which is 4. So as you can see, u is the 4x part, u prime is 4, and then you just plug it in. So let's say if we have e to the x squared, that means u is x squared, u prime is 2x. So it's going to be e to the u, or e to the x squared, times u prime, which is 2x. Now let's work on some more examples. Try these. E to the x to the 4th, e to the x to the 6th plus 3x to the 5th, and also e to the 4x plus 5. So this one is going to be the same thing times the derivative of x to the 4th, which is 4x cubed. And here it's going to be the same thing plus the derivative of the exponent. The derivative of x to the 6th is 6x to the 5th, and the derivative of 3x to the 5th is 15x to the 4th. For the last one, it's going to be the same thing. What is the derivative of 4x? The derivative of 4x is simply 4, and the derivative of 5, which is a constant, is 0. 4 plus 0 is just 4. By the way, the derivative, let's say, of 7x is simply 7. The derivative of 12x is simply 12. Here's why. If you use the power rule on x to the first power, it's going to be 1x to the 0. Anything raised to the 0 is simply 1. So you just get 12. Now what about logarithmic? Actually, before we get into logarithmic functions, there's something else that we need to do. What if you have to differentiate an exponential function other than e? So instead of the base being e, let's say if it's a number like 3. In this case, you want to use this formula. The derivative of a to the u is going to be equal to the same thing, a to the u times u prime times ln a. Now for e to the u, it was e to the u times u prime. It's really ln e as well, but it turns out that ln e is 1. But here is the real formula that we need to use. So it's going to be equal to the same thing, 3x squared times the derivative of x squared, which is 2x, times ln of a, and a is the base, which is 3. So knowing that, let's work on a few more examples. Try this one. 5x cubed and 7 raised to the 4x minus 3. So for this one, it's going to be the same thing times the derivative of x cubed, which is 3x squared, times ln 5. And for this one, it's a 7 raised to the 4x minus 3 times the derivative of 4x minus 3, which is 4, times ln of the base, which is 7. Now let's go over logarithmic functions. Let's start with natural logs. The derivative of the natural log of some function u is equal to u prime divided by u. So knowing that, what is the derivative of ln x squared plus 5x? So u is the function inside is x squared plus 5x, which means that u prime, the derivative of that is 2x plus 5. And so to differentiate it, it's just u prime over u, which is 2x plus 5 divided by x squared plus 5x. So let's work on some more examples. Let's try another one. What about ln x cubed minus 4x squared? What is the derivative of this function? So u prime, the derivative of the inside, is 3x squared minus 8x divided by the original stuff on the inside, which is x cubed minus 4x squared. Now what about this one? The derivative of ln x. The derivative of the inside function x is 1 divided by the original part of the inside, which is x. So you get 1 over x. So that's how you can differentiate natural log functions. Now what about logarithmic functions? Let's say log base a of u. Well, it's going to be similar to the last problem. It's u prime divided by u, but also ln a. So it's not just u prime over u, but you have to add the ln a part. So let's say if we want to differentiate log 3, x to the 4th. The derivative of x to the 4th is 4x cubed. The original part, the stuff on the inside, is just x to the 4th, and then times ln 3. And now we can reduce it. So this is the same as 4 over x ln 3. Now let's try another one. What about log 5 x cubed minus 7x? So u is equal to the stuff inside, which means u prime is the derivative, which is going to be 3x squared minus 7 divided by u, which is x cubed minus 7x, and then times natural log of 5. So now you know how to differentiate logarithmic functions. By the way, if you want more examples on differentiating exponential functions, logarithmic functions, just visit my channel. You can search for my videos on YouTube and look for my calculus playlist. I have more examples on this. Now let's go over the derivative of some trig functions. So make sure you memorize these formulas. The derivative of sine x is equal to cosine x. The derivative of cosine x is equal to negative sine x. The derivative of tangent x is equal to secant squared x. The derivative of the cotangent function is equal to negative cosecant squared x. The derivative of secant x is simply secant x tangent x. And finally, the derivative of cosecant x is negative cosecant x cotangent x. So anytime you differentiate one of the trig functions that start with a c, there's going to be a negative sign. If it doesn't start with a c, it's going to be a positive sign. Now let's talk about the product rule. Let's say if you wish to differentiate two functions that are multiplied to each other. It's going to be the derivative of the first function times the original of the second plus the original of the first times the derivative of the second. So let's apply that. Let's say if we want to find the derivative of x squared sine x. So we could say that the x squared part correlates to f and the sine x part correlates to g. So if f is x squared, that means that f prime, the derivative, is 2x. And if g is sine x, that means that g prime is the derivative of sine x, which is cosine x. And now all we need to do is just apply the formula. So f prime is going to be 2x, g is sine x. F is x squared, g prime is cosine x. And that's how you can find the derivative of the function using the product rule when you have two functions multiplied to each other. So let's work on some more examples. Go ahead and try this one. Find the derivative of x cubed times ln x. So let's differentiate the first part of the function, x cubed. The derivative of x cubed is 3x squared. And let's leave the second part the same way. So ln x. And then plus, let's leave the first part the same, x cubed, and then differentiate the second part. The derivative of ln x, we said it's 1 over x. And then simplify. So this is 3x squared ln x plus x cubed divided by x is x squared. And if we want to, we can take out the GCF, the greatest common factor, which is x squared. So we're left with 3 ln x plus 1. So this is the answer. Now what about differentiating a function that looks like this? What if there's 3 parts to it? Let's say we have x to the 4th times tangent x times e to the 2x. How can we differentiate this function? So we have an f, a g, and an h. So the derivative of f, g, h using the product rule, there's going to be 3 terms instead of 2. So you differentiate the first part, f, and leave the second 2 alone. And then you differentiate the second part, g, and leave the first and the last alone. And then you differentiate the last one, leaving the first 2 the same way it was. So let's begin. The derivative of the first part, x to the 4th, is 4x cubed. And g and h are going to stay the same. So tangent x times e to the 2x. Now we're going to leave the first part the same, x to the 4th. The derivative of the second part, g, is secant squared. And we're going to leave the third part the same way, e to the 2x. Now for the last part, f is going to stay the same and g will remain the same. The derivative of h, or e to the 2x, is e to the 2x times 2. So if we want to, we can factor the GCF, which is, we could take on e to the 2x, and we could take out x cubed from every term, if we want to simplify it. Or we can leave the answer like that. But that's how you would use the product rule if you have 3 things as opposed to 2. But let's go ahead and take out the GCF. So if we take out x cubed, e to the 2x, so this will be gone. We'll be left with 4 tangent x for the first part. And the second part, this will be gone. We'll have 1x left over, so it's going to be x secant squared x. And then for the last part, this will be gone. There will be an x left over. So it's going to be 2x tangent x. So you can also write the answer that way. The next concept that we need to cover is the quotient rule. The quotient rule is useful whenever you have a fraction containing 2 functions. So the derivative of f divided by g is going to be gf prime minus fg prime over g squared. So let's say if we want to find the derivative of the expression 5x plus 3 divided by 2x minus 4. So f is the top part of the function. F is 5x plus 3. G is the bottom part, 2x minus 4. So using the formula, it's going to be, let's write everything out. So if f is 5x plus 3, f prime is simply 5. The derivative of the constant 3 is 0. If g is 2x minus 4, g prime is simply 2. So let's plug in everything. So g is 2x minus 4, f prime is 5, minus f, which is 5x plus 3, times g prime, which is 2, divided by g squared, which is 2x minus 4 squared. So now let's simplify. Let's distribute the 5 and the 2. So 5 times 2x is 10x, and then 5 times 4 is 20, minus 2 times 5x, which is 10x, and 2 times 3 is 6. We don't need to FOIL the denominator, we can just leave it the way it is. Now we need to distribute the negative sign. So this is the same as 10x minus 20 minus 10x minus 6. So we can cancel these two, and negative 20 minus 6 is equal to negative 26. So this is the answer. Let's try another example. Go ahead and find the derivative of this function. So f is equal to x squared plus 4, and therefore f prime is 2x. G is equal to x cubed minus 5x, so g prime is 3x squared minus 5. So using the formula, it's going to be g f prime minus f g prime over g squared. So g is x cubed minus 5x, and then f prime is simply 2x minus f, which is x squared plus 4, and then g prime, which is 3x squared minus 5, divided by g squared, or x cubed minus 5x squared. So now let's distribute the first part. So 2x times x cubed is 2x to the 4th, and if we multiply it by 5x, that's negative 10x squared, and then minus. Now let's FOIL these two terms. So first we have x squared times 3x squared, that's 3x to the 4th power. And then these two are going to turn into negative 5x squared. And then we have 4 times 3x squared, which is plus 12x squared. And then 4 times negative 5, that's negative 20. And on the bottom, we're just going to leave it the same way. So let's distribute the negative sign. And at the same time, let's combine these two. Negative 5 plus 12 is 7, but positive 7x squared on the inside. So it's going to be negative 3x to the 4th. And then if you distribute this negative sign, negative 7x squared plus 20. So let's combine like terms. We can combine these two. That's going to be negative x to the 4th and negative 10 minus 7x squared, or negative 10x squared minus 7x squared, that's negative 17x squared, and then plus 20 divided by x cubed minus 5x squared, minus 5x and then squared. So this is the answer. Now the next concept that we need to cover briefly is the chain rule. So let's say if we have a composite function, that is a function within a function, f of g of x, and we wish to differentiate this function. This is equal to f prime g of x times g prime of x. So notice the pattern here. First, you differentiate the outside part of the function, that's f. And notice that you keep the inside the same way. And then you differentiate the inside function, which is g prime of x, and you connect them by means of multiplication. So let me show you how to apply this process. So let's say if we have the function x squared plus 4x raised to the 3rd. So g, the inside part, is x squared plus 4x. F, the outside part is x cubed. But the way you would do it, first use the power rule. Take the exponent, move it to the front. So we're differentiating the outside part, which is like f. Keep the inside part of the function the same. So we're not going to change x squared plus 4x. And then subtract 3 by 1, which is 2, and then differentiate the inside, which is 2x plus 4. So if you want to use this formula, you just need to realize that g is x squared plus 4x, and f is x cubed. But personally, I prefer to do it this way. I think it's easier. But differentiating f to find f prime, it's going to be 3x squared. And when you differentiate g to get g prime, it's 2x plus 4. So notice that the expression is f prime g times g prime. So as you can see, g prime is 2x plus 4, which is what we have here. G, the x squared plus 4, is inside of f. And you can see the parts on the outside. The 3 and the 2 are right here. But the inside part, the x, was replaced with g, because g is inside of f prime. So you can separate into two functions and get the same answer, but it's easier if you get used to the process of finding it. You can get the answer quickly. Let's try another example. Let's try this one, 5x minus 9 raised to the 6th power. So using the chain rule, we're going to take the exponent and move it to the front. So it's going to be 6, keep the inside the same, and then subtract the exponent by 1. 6 minus 1 is 5. And then differentiate the inside. The derivative of 5x minus 9 is 5. That's how you can do it the fast way. But for those of you who want to show your work, identify f of x and g of x. G of x is the inside function. That's 5x minus 9. F of x is the outside part, x to the 6th power. So using the formula, we know it's going to be, we know that the derivative of f of g of x is equal to f prime g of x times g prime of x. So first, let's write f prime. F prime is 6x to the 5th power, and g prime is simply just 5. So f prime, that's 6x to the 5th power, and g prime is 5. Now notice that we have f prime g of x. So we got to replace x with g of x. And g of x is this. So it's going to be 6, 5x minus 9 to the 5th power times 5, which is what we had before. So that's how you can apply the formula to get the same answer. So now let's work on some more chain rule problems. Try this one. What is the derivative of sine 4x? So first you differentiate the outside portion, sine. The derivative of sine is cosine, and you got to keep the inside part the same. So the angle of sine was 4x, therefore the angle of cosine will be 4x. So you want to work your way from the outside towards the inside. So then differentiate the inside function, 4x, which is 4, and that's the answer. Try this one, tangent x cubed. So first differentiate the outside part of the function. The derivative of tangent is secant squared, and then keep the inside the same. So this is going to be x cubed. And then finally differentiate the inside part of the function. The derivative of x cubed is 3x squared. Now what about this one? Sine tangent x to the 5th power. So let's start with the outside part of the function. The derivative of sine is cosine. And the inside part of sine will be the inside part of cosine. That's tangent x to the 5th. Next, let's work our way towards the inside. The next part we need to differentiate is tangent. The derivative of tangent is secant squared. And then keep the inside part of tangent the same. So the inside part of tangent is x to the fifth. So the derivative of tangent will have the same angle, or the inside part. And then let's move on further towards the inside. The derivative of x to the fifth power is 5x to the fourth. So this is the answer. Everything is multiplied to each other, by the way. Now what about this one? Cosine to the seventh power sine tangent x to the seventh. Try that one. So because we have an exponent, we need to rewrite it. I would rewrite it like this: cosine, sine, tangent, and so forth, all raised to the seventh power. It's going to be a lot easier if you do it this way. So first, we need to work on the exponent. Let's move the 7 to the front. So it's going to be 7, and then keep the inside the same. That is the entire cosine, sine, tangent x to the seventh. That has to remain the same. And then subtract the exponent by 1, so it's now going to be 6. So now that we finished with the outside part of the function, which was x to the seventh, now let's work our way towards the inside. So first we need to work with a cosine. The derivative of cosine is negative sine, and the inside part of cosine is this. So that's going to be the inside part of the negative sine function. It's going to be sine tangent x to the seventh. So now we're done with cosine. Let's move on towards sine. The derivative of sine is cosine. It's multiplied by everything else. And the inside part of that sine function is tangent x to the seventh. Now let's work our way in. Let's differentiate the tangent function. The derivative of tangent is secant squared, and then the inside part of tan is x to the seventh. Now let's move on to the x to the seventh on the inside, which is just 7x to the 6, and now we're done. So now you know how to differentiate problems using the chain rule. That's when you have a function inside of another function. Now let's spend some time talking about first and second derivatives. The first derivative is positive whenever the function is increasing. The first derivative is negative whenever the function is decreasing. And the first derivative is 0 whenever the function is constant or has a horizontal tangent. The function can increase in 3 ways. It can increase at a decreasing rate, at a constant rate, or it can increase at an increasing rate. And a function could decrease in 3 different ways. It can decrease at a decreasing rate, at a constant rate, or it can decrease at an increasing rate. The function is constant whenever you have a straight line, whenever it's horizontal. It can be horizontal at this point or at this point too. At those points you have a horizontal tangent. And the first derivative is equal to 0. Now what about the second derivative? What does that tell us? Whenever the second derivative is positive, that tells us that the first derivative is increasing. And when the second derivative is negative, that means that the first derivative is decreasing. So what kind of shapes do we have? The second derivative is positive whenever the graph is concave up. It looks like an upward U shape. And it's negative whenever the graph is concave down. The second derivative is 0 whenever the concavity changes. That may not be the only time it's 0, but when the concavity changes, it's definitely 0 at this point. So notice that the concavity changes here. The left side is concave down. We have the downward U shape. The right side is concave up. So this is the inflection point. That's when the second derivative is equal to 0, and that's when the concavity changes. Now let's consider this function. Let's call it f of x. When is the function increasing and when is it decreasing? The function is increasing whenever the graph is going up. So it's increasing in this region and in this region. Keep in mind, when the function is increasing, the first derivative is positive. The function is decreasing when it's going down, which is in those two locations. Now sometimes you need to write the intervals where the function is increasing and decreasing. So let's start with when it's increasing. So we said it's increasing here. That's between -3 to 1 using x values, and also beyond 2. So to write it using interval notation, it starts from -3, it stops at 1, and then union, it increases from 2 to infinity. Now the function is decreasing when the graph is going down. That's in these two locations. So we could say that it's decreasing from -infinity to -3, union 1 to 2. Now, what are the critical points in this graph? The critical points occur whenever you have a minimum, a maximum, or if you have a vertical tangent. So anytime you have a horizontal tangent, which occurs at the minimum or the maximum, the first derivative is equal to 0. Whenever the first derivative is equal to 0, those are critical points whenever you have a horizontal tangent. Also, if you have a cusp, which looks like this, here we have a vertical tangent. So the first derivative does not exist at this point, which is also defined as a critical point. So anytime you have a horizontal tangent or a vertical tangent, you have a critical point. So the critical points are, they occur at -3, at x equals 1, and at x equals 2. At -3 and 1, we have a horizontal tangent. At 2, we have a vertical tangent. So those are critical points. Now we talked about the max and the minimum. -3 is a relative minimum. It's the lowest point in this region. It's also called a local minimum. At 1, we have a local maximum. These are known as relative extreme values. And at 2, we also have a relative minimum. Now, what is the difference between a relative extreme value and an absolute extreme value? Do we have any absolute maximum values? Notice that this point is not the highest point of the graph. This part keeps going, so there's no limit to the highest point. Now, are there any absolute minimum? There is an absolute minimum value, and it's this point. That point is the lowest point on the graph. So the value at x equals -3 is not only a relative minimum, but it's also an absolute minimum because it's the lowest point. To make sure you understand that concept. Now let's focus on this local maximum. If you get a question that asks you where is the local maximum located, they want the x value. So you would say it's located at x equals 1. Now if they ask you what is the absolute maximum value, they're asking for the y value. The absolute, not the absolute maximum value, but the relative maximum value is 10. There is no absolute max in this problem. So the relative max is 10. Now, where is the absolute minimum located? We could say that it's located at x equals -3. And if they ask you what is the absolute minimum value, you would say it's equal to the y value of -5. Now let's move on to concavity. When is the function concave up and when is it concave down? So keep in mind the function is concave up when the second derivative is positive. The function is increasing when the first derivative is positive. Now it's concave up whenever we have an upward U shape. Here we have an upward U shape. This part is the downward U shape. and this is also a downward U shape as well. So from here to here, we could say it's concave up. So that's negative infinity to about, we can round it and say like -1. So negative infinity to -1 is concave up. It's concave down in this region, and it's also concave down here. But at the cusp, at 2, it's undefined. We can't say exactly what's happening there. So it's concave down, meaning that the second derivative is negative from -1 to 2, but not including 2, and then union 2 to infinity. The function is concave down at that point. Now, what is the inflection point? The inflection point occurs when the concavity changes. Here, it was concave up, and then here, it's concave down, which means that this is an inflection point. So the inflection point occurs at an x value of -1. So that's how you can find the inflection point from the graph. But sometimes, we may be given a function as opposed to a graph. How can we answer these questions if we're given a function? Well, let's find out. Now let's say that we have the function f of x is equal to x cubed minus 3x squared minus 9x plus 3. First, let's find the critical points, the intervals where the function is increasing, decreasing. Let's also find any relative extreme values, that is, relative maximum values and relative minimum values. And let's find the intervals where the function is concave up, concave down, and if there's any inflection points. So let's begin by finding the first derivative. This will help us to find the critical points. Whenever the first derivative is equal to 0, those x values are the critical points. And you can also find the intervals where the function is increasing, decreasing using the first derivative, and also the relative extreme values. The second derivative helps you to find the concavity and the inflection points. The derivative of x cubed is 3x squared, and the derivative of 3x squared is 6x. The derivative of 9x is 9. So let's set it equal to 0. So we need to factor this expression. Let's begin by taking out the GCF, which is 3. 3x squared divided by 3 is x squared. Negative 6x divided by 3 is negative 2x. Negative 9 divided by 3 is negative 3. So we have a trinomial with a leading coefficient of 1. What two numbers multiply to negative 3 but add to negative 2? This is going to be negative 3 and positive 1. So to factor it, it's going to be x minus 3 times x plus 1, which means that if you set them equal to 0, the critical points are positive 3 and negative 1. You need to set x minus 3 equal to 0, and you'll see that x is equal to positive 3. And if you set x plus 1 equal to 0, x is equal to negative 1. So we have the critical points. What do we do now? At this point, make a number line, putting it in order. Negative 1 comes before positive 3. Then test the signs. Pick a number that's greater than 3. Let's say 4. If we plug in 4 into the first derivative, will it be positive or negative? 4 minus 3 is positive. 4 plus 1 is positive. So the first derivative is positive when x is greater than 3. What about between negative 1 and 3? Let's try 0. 0 minus 3 is negative. 0 plus 1 is positive. A negative times a positive is equal to a negative. Now what about something less than negative 1, like negative 2? Negative 2 minus 3 is negative. Negative 2 plus 1 is negative. A negative number times a negative number is a positive number. So with this information, we can now answer the other questions. Now we said that the function is increasing whenever the first derivative is positive. The first derivative is positive in these two regions. So now we can write the intervals where the function is increasing. All the way to the left we have negative infinity, and to the right positive infinity. So the function is increasing in the interval from negative infinity to negative 1 union 3 to infinity. Now the function is decreasing whenever f prime is negative. So that is between negative 1 and 3. So that's how you can find the intervals when a function is increasing or decreasing if you're given a function instead of a graph. You need to make a sign chart. Now what about the relative extreme values? Whenever the derivative changes from positive to negative or from increasing to decreasing, notice that we have a relative maximum. And when it changes from negative to positive or decreasing to increasing, we have a relative minimum. So the relative maximum occurs at an x value of negative 1, and the relative minimum occurs at an x value of 3. So that's how you can find everything using the first derivative sign chart. Now, let's find the second derivative. The second derivative of 3x squared, the derivative of 3x squared is 6x. The derivative of 6x is 6. So this is the second derivative. Let's set it equal to 0, and let's solve for x. So x is equal to 1. So 1 is a potential inflection point. If the concavity changes sign, then 1 will be an inflection point. If it doesn't change sign, let's say if this was positive and positive, 1 is not an inflection point. But let's find out. So let's plug in a number that's bigger than 2. Bigger than 1. Let's try 2. 2 minus 1 is positive. And if we try a number that's less than 1, let's say 0, 0 minus 1 is negative. So it changes from negative to positive. So this is the second derivative sign chart. It's concave up when the second derivative is positive, and it's concave down when the second derivative is negative. So the function is concave up from 1 to infinity, and it's concave down from negative infinity to 1. And 1 is an inflection point. Now there's two theorems that you need to know. Rolle's theorem and the mean value theorem. Let's talk about Rolle's theorem first. So if the function is continuous on the closed interval a and b, and if it's differentiable on the open interval a and b, and if f of a equals f of b, then according to Rolle's theorem, there is some value c where c is between a and b, such that f prime of c is equal to 0. Now let's talk about what this means. Let's say f of a is 0 and f of b is 0. So here's a, here's b. There's some value c where the first derivative is equal to 0, meaning that we're going to have a horizontal tangent line. If we have a continuous function, there's no points of discontinuity. So we have to connect from a to b. And as you can see, at some point, we have a horizontal tangent where the first derivative is equal to 0. And that's the main idea of Rolle's theorem. As long as the function is continuous from a to b, and if f of a equals f of b, there's going to be a c value where the first derivative is 0. Now let's focus on the mean value theorem. By the way, if you're wondering what exactly does it mean for a function to be differentiable, let me answer that question. At this point, whenever you have a cusp, the function is not differentiable. It's continuous, but not differentiable. It's continuous in the sense that there's no jumps, there's no points of, the graph is not disconnected. But notice that the slope changes from a negative value because it's decreasing, and it instantly changes to a positive value. Whenever the graph makes a sharp turn, the function is not differentiable, which means that the derivative is not continuous, or the derivative does not exist at that point. So anytime the function has a sharp turn, the function is not differentiable at that point, which means that the derivative either is not continuous at that point or doesn't exist at that point. So now let's talk about the mean value theorem. Sometimes you might see it abbreviated as MVT. So the mean value theorem states that if the function is continuous on the closed interval a and b, and differentiable on the open interval a and b, then there is some value c between a and b such that f prime of c is equal to f of b minus f of a over b minus a. If you recall, this is the formula to calculate the average rate of change, and this is the formula to calculate the instantaneous rate of change. So there's some value c where the instantaneous rate of change is equal to the average rate of change. And if you recall, the instantaneous rate of change is the slope of the tangent line. The average rate of change is the slope of the secant line. So now let's think about what this means. So let's say we have a continuous function. Let's say this is a and this is b. The average rate of change is basically the slope of the secant line. The secant line is the line that touches the curve at 2 points. Now there's some value c somewhere between a and b where the slope of the tangent line, which touches only point c once, is equal to the slope of the secant line. As you can see, the tangent line and the secant line are parallel. So the mean value theorem is focused on finding that c value. Let's say that f of x is equal to x squared minus 2x plus 1. Find all numbers c that satisfy the conclusion of Rolle's theorem. And let's say the interval is from 0 to 2. So a is 0, b is 2. Now whenever you have a polynomial function or a quadratic function or even a linear function, it's going to be continuous on a closed interval and differentiable on the open interval. But you should always check to see if those two conditions are met, which it is in this problem. Now the next thing we need to do is show that f of a is equal to f of b. To do that, let's find f of 0. So let's plug in 0 into the equation. 0 squared minus 2 times 0 plus 1 is simply equal to 1. Now let's calculate f of 2. So 2 squared minus 2 times 2 plus 1. 2 squared is 4, 2 times 2 is 4. These cancel and we get 1. So f of a is equal to f of b. So therefore there has to be some c value that is between a and b, that is between 0 and 2, such that f prime of that number is equal to 0. So what we need to do is find the first derivative and set it equal to 0. F prime of x is 2x minus 2. If we take out a 2, we can see that we have the factor x minus 1, which means x is 1. And is 1 between 0 and 2? Yes, it is. So that's our c value. So there is a number c such that f prime of c is equal to 0, and c is between 0 and 2. So that's how you can solve for c using Rolle's theorem. Let's try another problem like the last one, but using the MVT, mean value theorem. So f of x will be equal to 3x squared plus 2x plus 5 in the interval -1 to 1. So we got to find c, and according to the mean value theorem, we know that f prime of c is equal to f of b minus f of a divided by b minus a. So how can we apply this formula? On the left, to find f prime of c, we need to find the first derivative. F prime of x is going to be equal to 6x plus 2. On the right, we need to find the average rate of change. A is -1, b is 1. So we got to find f of 1 minus f of -1 divided by 1 minus -1. F of 1, if we plug it into the first formula, 3 times 1 squared plus 2 times 1 plus 5 is equal to 10. And if we plug in -1, that's going to be 3 minus 2 plus 5, 3 plus 5 is 8, minus 2 is 6, and 1 minus negative 1 is 1 plus 1, which is 2. 10 minus 6 is 4. 4 divided by 2 is 2. So 6x plus 2 is equal to 2, which means if you subtract 2 from both sides, 6x is 0 and x is 0. So the c value is equal to 0. So notice that this c value is indeed between a and b. It's between negative 1 and 1. So f prime of 0 is equal to the average rate of change between negative 1 and 1. Notice that the average rate of change is 2, and the instantaneous rate of change when you plug in 0 will also be 2. So that's how you can apply the mean value theorem. You want to find the first derivative, set it equal to the average rate of change, solve for x, and that x value is your c value. Now let's talk about rectilinear motion. Sometimes you'll see calculus and physics come together. S of t represents the position function, and v of t represents the velocity function, and a of t represents acceleration. The velocity function is the rate of change of the position function. So to find the velocity, you can find the first derivative of the position function. The acceleration function is the rate of change of velocity. So if you find the derivative of the velocity function, that's equal to the acceleration, which is the same as the second derivative of the position function. So the position function simply tells you where the object or even the particle is located. Typically, the position function is used to describe its relative to the x-axis. So let's say if s of 1 is 3, the particle is located at an x value of 3 when t is 1. Let's say if s of 2 is negative 5, that means it's on the left side. At t equals 2 seconds, the particle is like maybe 5 meters from the origin on the left side. So the position function just tells you the location of the particle. Now the velocity tells you like where it's moving. For example, if the velocity is positive, it means that the function, or the particle rather, the particle or the object is moving to the right. If the velocity is negative, the particle is moving towards the left. And if the velocity is 0, it can mean one of two things. The particle is at rest. It could be at rest for a very short time or a long time. If it's at rest for a short time, then you say it's at rest. If it's equal to 0 for a short time instead of a long time. So let me say it again. If v is equal to 0 for a long time, it's at rest. If it's equal to 0 for a short time, then chances are it's probably changing directions. So I just want to clarify that. So let's say if we have a velocity function. Actually, let's use position. Let's say this is the position function. Keep in mind, the slope of the position function is equal to the velocity. So here, notice the slope is 0. That means the velocity is 0. And it's 0 for a long time. So here, the particle is at rest. Here, the slope is positive, which means the particle is moving to the right because velocity is positive. Here, it's decreasing. The slope is negative, so the particle is moving to the left since the velocity is negative. And here, it's positive again, so it's moving to the right. But at this point, notice that we have a horizontal tangent. So the velocity is equal to 0 temporarily, which means the particle is changing direction. So here it's at rest for a long time. Here it's equal to 0 for a short time, so it's changing direction. Now what about the acceleration? If the acceleration is positive, it means that the velocity is increasing. And the acceleration, if it's negative, it means that the velocity is decreasing. Now, if the acceleration is equal to 0, that means that the velocity is constant. Or the velocity could be 0, a constant 0 value. Whatever it is, the velocity is just not changing. It could be negative, positive, 0, but it's just constant. So on a velocity time graph, it will look like a straight line. Now the last thing that we need to know is when the particle is speeding up and when it's slowing down. The particle, let me start on a new page. The particle is speeding up whenever the acceleration and velocity vectors have the same sign. So when the acceleration is positive and the velocity is positive, it's speeding up. Or when they're both negative. It's slowing down when the acceleration and velocity have opposite signs. One is positive and the other is negative, and vice versa. Now let's say if we have a position function, s of t, and is equal to t to the third power minus 9t squared plus 24t minus 7. So first question, what is the velocity function? To find the velocity function, find the derivative of the position function. So it's 3t squared minus 18t plus 24. So they ask you, what is the velocity of the particle at t equals 2? Simply plug in 2. 2 squared is 4 times 3 is 12. 18 times 2 is 36. 12 minus 36 is negative 24 plus 24. That's equal to 0. So the velocity is 0 at t equals 2. Now, when is the particle moving to the right and when is it moving to the left? To answer that question, find the velocity function, set it equal to 0, and solve for t, and make a sign chart. It's the same as finding the critical points. So let's take out a 3 first. This is going to be t squared minus 6t plus 8. And to factor this expression, two numbers that multiply to 8 but add to negative 6 is t minus 2 and 4. Negative 2 times negative 4 is positive 8, but negative 2 plus negative 4 adds up to negative 6. So the 2 points of interest are 2 and 4. So that's when the velocity is equal to 0. We got one of those already. Now let's make a sign chart. When t is 5, 5 minus 4 is positive, 5 minus 2 is positive. And let's plug in a number between 2 and 4. Let's say 3. 3 minus 2 is positive, but 3 minus 4 is negative. And if we plug in a number less than 2, let's say 0. 0 minus 2 is negative, 0 minus 4 is negative. Two negatives make a positive. Anytime the exponents of these factors are odd, the signs will change across that value. If it's even, then it won't change across that value. So the particle is moving to the right whenever the velocity is positive. Now for these type of problems involving time, time doesn't have any negative values. So you need to start at 0 and go towards infinity. So the particle is moving to the right between starting from 0, so it includes 0, to 2, and then union 4 to infinity. It doesn't include 2 or 4 because the velocity is not positive at 2 and 4. It's 0. So keep that in mind. Now it's moving to the left between 2 and 4. It's moving to the left whenever the velocity is 0. And the particle changes direction at 2 and 4. That's when the velocity is 0, and as you can see, the sign changes at those points. So now you know how to find when the particle is moving to the right or to the left and when it's at rest. So it's temporarily at rest for a short time at 2 and 4. It changes direction at that time. So now what is the acceleration function? The acceleration function is the derivative of the velocity function. It's 6t. I want to keep this sign chart. It's going to be useful later. But the acceleration function is 6t minus 18. So let's set it equal to 0. And let's find when the acceleration is positive and when it's negative. So the points of interest are 3. So from 3 to infinity, the acceleration is positive, which means that the velocity is increasing at that point. And from 0 to 3, the acceleration is negative, which means the velocity is decreasing. Now, using these two sign charts, when is the particle speeding up and when is it slowing down? Feel free to pause the video and see if you can answer that question. Let's begin by combining the two sign charts into a single sign chart. So let's combine these two values, 2, 4, and 3. So we're going to have 2, 3, 4, infinity, and 0. On top, we're going to put the signs for velocity. On the bottom, the signs for acceleration. So the velocity is positive between 0 and 2, and it's positive between 4 and infinity. Between 2 and 4, the velocity is negative. So we don't need this anymore. Now, the acceleration is negative between 0 and 3. And the acceleration is positive between 3 and infinity. Now, keep in mind, we said that the particle is speeding up whenever the velocity and acceleration have the same sign. Here it's both negative and here it's both positive. So it's speeding up at these two values, between 2 and 3 and 4 to infinity. So let's write that in interval notation. So it's speeding up between 2 and 3, union 4 to infinity. And it's slowing down whenever the velocity and the acceleration have opposite signs. So that is including 0 to 2, union 3 to 4. Now, by the way, how can we determine the total distance traveled by the particle and the displacement of the particle? Let's say if we want to find the displacement of the particle in, let's say, the first 5 seconds. And also the total distance traveled in the first 5 seconds. To find the displacement, it's simply equal to the change in position, s of 5 minus s of 0. And you would use this function to find it. Now, I'm not going to actually get the answer, but I'm just going to tell you what to do to find the answer. Now, to find the total distance traveled, you need to take into account when the particle changes direction. That's when the velocity is 0. That's at 2 and at 4. So what you need to do is find the distance that it traveled in the first 2 seconds. So you take the absolute value of s of 2 minus s of 0 plus the distance that it travels in the next 2 seconds, that is between 2 and 4. So it's going to be s of 4 minus s of 2, absolute value. And then you want to end at 5. So you want to find the displacement between 5 and 4. And just make sure it's positive. So notice that the particle is moving to the right between 0 and 2. So this answer will be positive. But between 2 and 4, it's moving to the left. So this is negative, but we need to make it positive. So we add the absolute value sign. And from 4 to 5, it's positive. It's moving to the right. So that's how you would find the distance. You see, for displacement, whenever the particle moves to the right, the displacement is positive. When it moves to the left, it's negative. But distance is always positive. So while it's moving to the left, we need to make that value positive. And that's why we use the absolute value sign. Now let me help you to understand the concept between distance and displacement conceptually. So let's say that the particle is at the origin at a position of 0. It moves 7 meters to the right, and then it moves 13 meters to the left, and then 2 meters to the right. What is the displacement of the particle? So every time it changes direction, we need to take that into account. So to find the displacement, you can simply add the individual displacements. That's positive 7, negative 13, positive 2, which is equal to negative 4. That's the displacement. Now to find the total distance, what you would do is add the absolute value of each of those values. So the absolute value of 7 plus the absolute value of negative 13 plus the absolute value of 2, which is 7 plus 13 plus 2. So the total distance traveled is 22. So now you understand why we were using the absolute values in the other situation, in the other problem. It traveled a total of 22 meters. So you just add these numbers and make each value positive. So let's check using the number line. If we travel 7 meters to the right, we're going to be at position 7. And if we go 13 meters towards the left, 7 minus 13 will take us to position negative 6. And if we travel 2 meters to the right from that, we will end at position negative 4. So as you can see, the change from 0 to negative 4, the change is negative 4. That's the displacement. So hopefully this helps you to distinguish displacement and distance. Distance is scalar. It's always positive. Direction is not important for distance. Displacement is a vector. Direction is important. Displacement can be positive or negative. Now what about speed? What's the difference between speed and velocity? So let's say if the velocity function is 2t minus 9. What is the speed of the particle at t equals 3? So first find the velocity at 3. It's going to be 2 times 3 minus 9, which is negative 3. But the speed at 3 is positive 3. Speed is scalar, velocity is a vector. Speed is always positive, velocity can be positive or negative. Speed has magnitude only, but velocity has magnitude and direction. So make sure you understand that speed is simply the absolute value of velocity. Now let's move on to a new topic, antiderivatives. We know that the derivative of x cubed is equal to 3x squared. The antiderivative of 3x squared is therefore x cubed. So to find the antiderivative, or the integral of a function, it's basically just the opposite of differentiation. So how can we go from here to here? What sort of method should we use? The antiderivative of a function x to the n is equal to x to the n plus 1 divided by n plus 1. So what you want to do is find the antiderivative of x squared. Rewrite the constant 3, and for x squared, add 1 to the exponent. 2 plus 1 is 3, and then divide by that number. So you just get x cubed. This is called an indefinite integral. Anytime you have an indefinite integral, you need to add a constant to it, plus c. So let's work on some other examples. What is the antiderivative of x to the 4th dx? This is going to be x to the 5 divided by 5 plus c. So the antiderivative of, let's say, 8x cubed is 8x to the 4th divided by 4 plus c, and this reduces to 2x to the 4th plus c. To find the antiderivative of a constant, simply add an x to it, because the derivative of 5x is 5. So the antiderivative of 5 is 5x. Now what about the antiderivative of the square root of x? What can we do in this example? So first, rewrite it. and then use the power rule. Add 1 to the exponent. 1/2 plus 1 is the same as 1 over 2 plus 2 over 2, which is 3 over 2. Now, instead of dividing it by 3 over 2, this is the same as multiplying it by the reciprocal, or 2 over 3. So this is the answer. Let's try another example like that. Find the antiderivative of the 7th root of x to the 5th. So first, rewrite it. This is 5 over 7. Add 1 to the exponent. 5 over 7 plus 1. 1 is the same as 7 over 7, so this is 12 over 7. So it's going to be, once you integrate it, you don't need the integration symbol anymore. So this is going to be x to the 12 over 7, and instead of dividing it by 12 over 7, let's multiply it by 7 over 12, plus c. So that's how you can integrate a radical function. Now what about rational functions? What's the antiderivative of 1 over x squared? So first, rewrite it, and then add 1 to the exponent. So it's going to be x to the negative 1, and then divide by that result. So this is the same as negative 1 over x plus c. Try this one, 5 over x cubed. So I'm going to move the constant to the front and rewrite it. So let's add 1. Negative 3 plus 1 is negative 2, and then divide by that result. So it's negative 5 over 2x squared plus c. Now what about this one? What's the antiderivative of 1 over x dx? If we rewrite it, if we add 1, this is going to be 0 over 0, which is undefined. So for this one, you just have to know that this is equal to ln x. The derivative of ln x is 1 over x, so keep that in mind. And then there's the trig functions. The derivative of sine is cosine. So the antiderivative of cosine is positive sine. The antiderivative of sine is negative cosine. The antiderivative of secant squared is tangent plus c. The antiderivative of cosecant squared is negative cotangent plus c. And the antiderivative of secant tan is simply secant x. And the antiderivative of cosecant cotangent x is negative cosecant x. Now we said that the antiderivative of 1 over x is the natural log of x. So what is the antiderivative of 1 over x minus 3? If you see this, it's simply ln x minus 3 plus c. The antiderivative of 7 over x plus 2 is simply 7 times the natural log x plus 2. And make sure you use an absolute value for these things. Now what about exponential functions? Let's say e to the 3x. We know that the derivative of e to the 3x is simply e to the 3x times 3. But for integration, instead of multiplying by 3, we need to divide by 3. It's going to be e to the 3x divided by 3 plus c. And if you find the derivative of this function, it should give you the original. This only works if the exponent is a linear function, like 3x, 5x, 7x plus 2. If it's quadratic or cubic or anything else, it does not work. You can't integrate it that way. So the integration of e to the x squared does not equal e to the x squared over 2x. Because if you were to find the derivative of this, you would have to use a quotient rule, and it won't give you the function that you started with. So just keep that in mind. So let's work on some more examples. Go ahead and find the antiderivative of the following functions. So make sure you only divide it by a constant. If you divide it by a constant, then it's going to work. If there's a variable in the bottom, it won't work. The antiderivative of e to the negative 7x is going to be the same thing, but divided by the derivative of negative 7x, which is negative 7. For the last one, it's going to be the same thing, but divided by the derivative of 4x plus 5, which is 4. So that's how you can find the antiderivatives of simple exponential functions. Now, what if we were to see a problem like this? Let's say if you see numbers on the integrand symbol. This is the lower limit, the upper limit. This is called a definite integral. And your final answer is not going to be a function in terms of x. It's going to equal a number. So first, let's find the antiderivative. The antiderivative of x squared is x cubed over 3, and the antiderivative of negative 4 is negative 4x, evaluated from 1 to 2. So first, we're going to plug in the top number into this expression. So that's 2 to the third divided by 3 minus 4 times 2. Next, let's plug in the number on the bottom into the same function, and then let's evaluate it. So this is going to be 8 over 3 minus 8 minus 1/3 plus 4, if you combine these two. 8 over 3 minus 1 over 3 is 7 over 3. Negative 8 plus 4 is negative 4. Negative 4 is the same as 12 over 3. So now that we have the same denominator, we can add the two fractions. So the final answer is negative 5/3. So that's what you need to do if you have a definite integral. Let's try another example like that. Go ahead and try this one. Find the value of the definite integral from 0 to 3. So first, let's integrate this function. This is x to the first power, so it's going to be 5x to the second power divided by 2. The antiderivative of a constant, simply add x to it. So now let's plug in 3. This is going to be 5 times 3 squared over 2 minus 2 times 3. And then minus, now let's plug in the lower value. Once we plug in 0, the whole thing is going to be 0. 0 squared is 0, 2 times 0 is 0. 3 squared is 9, times 5 is 45, and 2 times 3 is 6. So 6 over 1, we can multiply the top and bottom by 2, giving us 12 over 2. And 45 minus 12 is 33. So the answer is 33 over 2. Now, how can we find the value of the indefinite integral e to the x squared times x? Now, we can't integrate this function by itself, but because there's an x here, there's a certain technique that we can use to find the value of the indefinite integral, and that is u substitution. We want to set u equal to x squared. If we do that, du is going to be the derivative of x squared. It's going to be 2x times dx. Next, let's solve for dx. Dx is du divided by 2x. Our goal is to replace all the x variables with u variables, making the expression easier to integrate. So let's replace x squared with u, and let's replace dx with du over 2x. So notice that this variable cancels, which is good. And let's move this constant to the front. So what we now have is 1/2 antiderivative e to the u du, which we can integrate. The antiderivative of e to the u is simply e to the u. Now the only thing we need to do is replace u with what it was in the beginning, that is x squared. So the final answer is equal to this expression. So that's u substitution. Now let's try one more example. This is going to be the last example of this video. Let's use u substitution to find the integration of this expression. So should we make u equal to x or ln x? If we make u equal to x, du is going to be equal to 1 dx, which won't help us to get rid of the x in ln x. So let's make u equal to ln x, so that du is 1 over x dx. And solving for dx, let's multiply both sides by x. So dx is equal to x du. So now, let's replace ln x with u, and let's replace dx with x du. Our goal is to get these two to cancel. So now we just got to find the antiderivative of u, which is going to be u squared over 2 plus the constant c. Now the last thing we need to do is replace u with ln x. So it's 1/2 ln x squared plus c. So this is the answer. So that's just a brief overview of u substitution. By the way, all these different examples that you've encountered in this video, if you want to find more practice problems to improve your skills, just check out my channel and you can look for my calculus playlist and you can find specific topics that tailor your needs. So that is it for this video. If you really appreciate the value of this video, feel free to comment below. Feel free to like this video also. You can subscribe to it as well, share it with your friends, or if you want to, you can even donate at my channel page. So thanks again for watching and have a great day.